So thank you, Carlos, for the introduction. And I just want to say I'm very glad to be here showing this work, which was done in collaboration with Stefano Barbero, Emanuel Bellini, and Carlos Sana, and myself. So basically, what we wanted to show here, or what we wanted to study here, was how this new trend of asymptotically faster algorithms for solving polynomial systems behave in practice. So we implemented them, we summarized them under the same notation, and we measure some practical complexities. So let me start by describing the main problem here, which is the problem of solving system of polynomial equations over finite field. So as an input, what we are given is a set of n polynomials in n unknowns, where the coefficient of the polynomial lies in a finite field. And then what we want to find is just a vector, one solution such that the evaluation of every polynomial in the same vector is equal to 0. Very briefly, I'm gonna say why this problem is important in cryptography, and the main reason is because it's an NP-complete problem, so that any decisional problem can be modeled as a system of polynomial equations. It has a very tight application to what we call multivariate crypto, where the main problem, where the main problem here is the problem precisely of solving system of polynomial equations. And I would say in the whole cryptography spectrum, well, we have what we call algebraic attacks. And it's this kind of attacks that we can use to attack almost everything. And basically an algebraic attack is just a way to take a cryptographic construction and model it as a system of polynomial equation in such a way the solution of the system of polynomial equation or one solution leads to a break in the scheme we are studying. So this is the implication of this problem in cryptography. And there are many algorithms to solve this problem so far. The simplest one is a brute force. It's just given a system of polynomial of equations in n variables. What I'm gonna do is just to test all the possible vectors of length n, and then to check if any of them is a solution to the problem. So the complexity of this problem over F2, or Boolean polynomials, is given by this equation. But then we have more algorithms. We have something that we call direct linearization, which basically is instead of considering the polynomials as polynomials, just take every monomial and consider it as a variable. In our very restricted condition, you can solve by only performing linear algebra. And then if you cannot, then you can still use the monomials in the polynomial ring to generate more equations. And then for every monomial that you multiply by a polynomial you were given in the input, then you generate more monomials. And then again, up to certain conditions, you can again use linear algebra to solve the system of polynomials. We have Grosvenor basis algorithms, where the main idea here is just given a set of input polynomials. What we want to compute here is a Grosvenor basis. I'm not going to define what a Grosvenor basis is, but for the purpose of this problem, a Grosvenor basis is kind of a set of polynomial associated with the input polynomial such that find a solution in this set of polynomial over a specific monomial order is very easy to find. So we are given the input, we compute a Grosvenor basis, and finding a solution to the Grosvenor basis is easy. And the solution to the polynomials of the Grosvenor basis is the same solution of the initial system of polynomials. We have hybrid approaches. Here we combine brute force. So we search part of the solution, and then we either use a different algorithm to compute the rest of the solution, or we check the consistency of the remaining system. And also we have special algorithms. For instance, when we have more variables than equations, then we can do several things. We can either fix some variables at the beginning, or we can transform this system into a system that has the same number of equations and variables, but less variables. Or when the number of variables is something like is quadratic in the number of equations, then we have some polynomial time algorithm for solving for finding a solution of a system of polynomials. So yeah, in several cases or a particular regimes, it could happen that some of these algorithms are more efficient than brute force, but in general, none of them is asymptotically faster than brute force, meaning that in the asymptotical complexity of any of these algorithms, in the general case, not in any particular case, you have a factor of 2 to the something times n, where that something is always greater than 1. Yeah, so it was like this until 2017, when Lokhstanov, Patur, Tamaki, and Williams came out with this new idea. And they proposed an algorithm that basically check if a given system of polynomial equation has a solution or not. And this algorithm can be easily converted into an algorithm to find a solution to a system of polynomial or a finite field. And they proved that the asymptotical complexity, when you remove all the polynomial factors, is something like 2 to the something times n, where that something is less than 1. And we're going to see in detail how this algorithm works, not in detail, but the main ideas of how this algorithm works and what is the complexity of it. And then 2 years later, these guys, Georg Klum, Kasky, and Williams again, improved the idea, the initial idea of Lokhstanov and the others, and they came out with a different algorithm. And in this case, the main algorithm, what it does, it just take an input of polynomials, and then it computes the parity of the number of solutions. So at the end of the day, the main algorithm what it does, it outputs 0 or 1. It outputs 0 if the number of solutions of the initial system of polynomials is odd, and it outputs 0 if the number of solutions of the initial system of polynomial is even. And this can also be turned into an algorithm to solve or to find a solution to the initial system of polynomials. And last year, Dinur proposes 2 algorithms. The first one is, again, a parity counting algorithm, but a bit more efficient asymptotically than the one by Georg Klum et al. And then a more direct algorithm with a better complexity analysis, where he goes directly to find the solution of the system, and he doesn't go through the parity to find the solution. So this is what we're going to see here. So this talk is divided in 3 main parts. In the first part, we're going to briefly show what are the main techniques used in these 4 algorithms, what they have in common. And then we are going to try to show the main ideas of the algorithm for any of them very briefly. And finally, I'm going to show the practical results we obtain while implementing this algorithm in C. So the main object here is just a Boolean function. So a Boolean function is just a function from f2 to the n to f2. And it can be represented as a polynomial like this, where every monomial, every monomial is square free, meaning that the exponent of every variable in any monomial is either 0 or 1. And there are 2 ways of representing a Boolean function as a binary vector of length 2 to the n. One of them is called the algebraic normal form, and the other one is called the truth table of the Boolean function. So in the algebraic normal form, what we store is basically every coefficient of the polynomial under consideration. So the entries of the vectors are indexed by vectors in f2 to the n, and the coordinate corresponding to a vector a is just going to be the coefficient of the monomial x to the a, where x to the a is defined like this. On contrary, on the truth table, the coordinate corresponding to a vector b, corresponding to a vector a, is going to be the evaluation of the polynomial in that vector. So both are binary vectors, both have the same length. And what is very important here is that there's an algorithm that given one of the forms, give you the other one, and the other way around. And for the purpose of this talk, we're going to call this algorithm the zeta transform, and it's going to be denoted by this. So as I said, whenever you have a function and you apply the zeta transform to the algebraic normal form, you get the truth table. And if you input the truth table of a Boolean function, you get the algebraic normal form. So you have this, and it's very important to remember for the purpose of this talk that the complexity of this transformation is something of the order of m times 2 to the n, where n here is the number of variables. Another key, let's say, procedure of the algorithms used is that what we call the interpolation of a Boolean function. So I'm going to define it here. I'm not going to show how it works, but what it does. So basically, what we are giving as input here is something that we call a partial truth table of a Boolean function. And a partial truth table is basically not all the evaluation of the function, but some of them. Additionally, we require that the set of vectors satisfying a condition here. I'm not gonna go into the detail of what this condition is, but it's not for all vectors, not for all sets we can interpolate, but for some set of vectors. And what we want to compute, what the interpolation computes here is the whole truth table. So it goes from a partial truth table in a special set to the whole truth table, or representing the Boolean function. It's a very important procedure. And inside this procedure, we have to apply the zeta transform, and this is the more complex step of this algorithm, so that the complexity of this algorithm is n times 2 to the n again, where remember, n is the number of variables in my Boolean function. And this is very important, and it's basically the key of all the algorithms we're going to show, and it's the following. If you started with a Boolean function of degree d, then in this set here, I'm going to tell you what is the information you need so that you can compute the whole truth table, of the Boolean function f. And the information you need is a set of evaluation of f in a set of vectors, where this set of vectors satisfy that over the set of all vectors with Hamming weight less than d. So the only information you need in order to compute the truth table of a Boolean function of degree d are the partial truth table in the set of vectors of Hamming weight less than d. This is very important, and I want you to keep in mind this up to the end of this talk, because it's the main, one of the main steps in every algorithm. So also these algorithms make use of this polynomial that we are going to define as the characteristic polynomial of a system of polynomials. So given a set of polynomials P1 up to Pm, we can get another polynomial f defined in this way. Why this polynomial is relevant here? For several reasons. First, whenever this polynomial is equal to 1, then we know we found a solution to the system of polynomials. So in principle, what we wanted to do here is just to compute the truth table of the polynomial f, and then see for which values this polynomial f is equal to 1, and then we just found a solution. But remember from previous slide that the only information that I need is the evaluations of all the vectors with Hamming weight less than d. So the problem with this polynomial is that the degree of the polynomial is very high. So at the end, I would need like a very huge amount of vectors. I mean, 2 to the n vectors evaluation in order to compute the truth table. So I don't have any gain here. So we turn to use a different polynomial. So this polynomial is G, and it's defined in this way. So basically, G now doesn't have n variables, but n minus n1, and it's defined in this way. So you fix one vector of length n minus 1, and you evaluate the polynomial f in all the remaining variables, and then you add them together. The main property of this polynomial is the following. Whenever this polynomial is 1, then we know that the polynomial we wanted to find the ones is 1 for at least one vector c. So if we are able to find this, we already know this b making g equal to 1 is already part of one solution. We don't know what solution it is part of, but it's part of one solution. So this is the importance of this polynomial j. And more important is that, so this is just what I said before, the degree is a bit smaller than the polynomial f, but it's still very high, right? It's still very high. Remember, we want to find for what vectors this polynomial is equal to 1. So we want to interpolate, and to interpolate, we want to find the evaluation for all the vectors with Hamming weight less than the degree. So if the degree is very high, then we are not gaining anything here. Another property that this polynomial have is that when you add together all the images of this polynomial, what you have is the addition of all the images of the initial polynomial f, and this addition is, of course, modulus 2. So at the end, what you have here is the parity of the number of solutions. And this is what the first two algorithms this is what the York and Dinur's first algorithm wants to estimate, which is the parity of the number of solutions. So a quick summary here. So these algorithms wants to, at the end of the day, all what they want to do with different ways is just to estimate something like J, right? I want to estimate precisely the truth table of J. And for that, I'm gonna use a polynomial tilde J, which approximates my initial polynomial. But I want this polynomial to have a low degree. Why low degree? Because if it has low degree, I can compute the partial truth table and then interpolate it. And then if it approximates well J, then I can do something with J. This is the main idea. So in Yorklum, what we want to do is produce many tilde J's so that we can very precisely, with overwhelming probability, compute every value of J. And the same is done here in Dinur's first, but in a different way. And in the second algorithm of Dinur's is a bit different. Just with a few approximations, we want to somehow find a solution. Just let's keep it like this by now. And Loxanov is a bit different. He wants to approximate a different function. The function he wants to approximate is the function b, defined like this. So basically, it is the addition of some evaluation of the characteristic polynomial f, And then whenever this guy is equal to 1, we know that some of these are equal to 1, where this SC is something that is chosen uniformly at random. So basically, I want to compute the truth table of this because whenever this guy is 1, I know some of this is 1, even though I don't know which one is 1, but I know that there's a solution. So I can just turn this into an algorithm to check if a given system has a solution or not. So we talk approximations. We said we wanted to compute tilde j approximating a very key function here. And in this slide, what I want to show you is what are the techniques we use to approximate a polynomial, and then basically what the approximation of Boolean function means, basically. So we're gonna say this polynomial tilde f approximate f if for every vector the probability that these two values are equal is very close to 1. If it's very, very, very close to 1, we say it's a good approximation, otherwise it's not a good approximation. And the randomness here is coming from the generation of f. So we perform a random process to generate tilde f, and then we compute this probability. And yeah, the way how we randomize tilde f is in the following way. So basically, we take, we can focus here, we take the input polynomials and we produce, let's say, few random linear combinations, and we call it RIs. And then we use the RIs as if they were the initial PIs. But the difference here is, of course, these are random linear combinations, and we have less polynomials than initial. So we expect that the degree of this guy is smaller than the degree of f. Of course, the degree of this approximation is going to be less than d times L, where d is the degree of the initial polynomials. We're assuming that the initial polynomials have degree d. And then whenever the full polynomial f is equal to 1, the approximation is equal to 1. And in the other case, when this guy is 0, then the approximation is going to be 0 with overwhelming probability. And then we say, wow, we have a good approximation of the polynomial we wanted to approximate, right? Because this is going exponentially faster to 1. But even more, remember what we want at the beginning was approximate tilde j, and then a way to approximate tilde j is given by this equation here. So this, if this is the approximation of f, this is the approximation of tilde j. And with the log standoff is a bit different. We want to approximate the v, so we use this definition. So even though this is a good approximation, we still have a lot of vectors we want this to be equal to. And then we still expect that for many values, these two aren't equal, right? So we have an exponentially close approximation, but we also have an exponentially number of things that have to be equal. So we still expect some errors. And then what this algorithm basically does, they say, okay, we have errors, but then if we repeat the approximation of tilde j too many times, and then somehow we manage to compute for a given b how many of these are equal to 1, then we set up a, let's say, a bound here, and we say whenever this many of these are equal to 1, I mean, if the number of approximation I produces are equal, evaluating a vector b is equal to 1, and that number is greater than t0, then I'm gonna say this j should be this, and then I'm gonna work with this j, and then I'm gonna finish my algorithm. And this is the main idea on many of them, right? Yeah, this is the idea. So yeah, I said that I'm gonna start by describing all of the algorithm. I'm gonna start by log standoff. So here we are assuming the input polynomials have degree D, and the idea is the following. So forget a bit about these parameters. You remember that there are some parameters here, and we are going to repeat this loop S times, where S is just the number of JT, the polynomials that I'm going to use to approximate J. Well, in this case, it's not J by V, but V. So basically, here in the first step, this is, I'm gonna basically compute this polynomial here, and I'm gonna do it symbolically, so that at the end of the day, what I'm gonna compute is are all the polynomials, sorry, all the coefficients of this polynomial V, sorry, of this polynomial V. And then just a technical detail here, for each value of C, we choose a different F tilde, we choose a different approximation. And then basically we compute the, let's say, all the coefficients of the polynomial symbolically, and then we use theta transform for going to the algebraic normal form, to the truth table. And once we have the truth table, well, we store for every iteration of the loop, and then we do what I just said, right? We just, for every B, we check for how many approximation polynomials the value of tilde B was equal to 1. And whenever we had more than 40% ones, then we said we output true, meaning that we said that the given system of polynomials have a solution. If none of the vectors in this set satisfy this condition, then we said the input polynomial has no solution, so we output false. So there are two main steps here in this algorithm. I'm not going to go into the details here. Just remember the first loop is the most costly one, and the second loop. So for the first loop, we want to compute is what is the cost of doing this symbolic computation here, and then this symbolic computation we have to do it around 2 to the n times, because we have to do it for this guy. And then basically to estimate the complexity, we set up the parameters so that T1 is approximately the same as T2. And then we end up with a complexity which is exponentially faster than brute force. So as I was telling before, for quadratic polynomials, we have a complexity of 2 to the 0.87n, something like that. And for non-quadratic polynomials, the complexity is something like this. So we already here, we show that we exponentially outperform brute force. So your clue is, again, we have input polynomials of degree D. And here I want to you to focus a bit in the definition of this set. This is the set where we want to compute the partial truth table. It's basically all the vectors such that its Hamming weight is less than T. And the main goal here, again, is just to compute the truth table of J, very precise. And again, we are gonna generate a lot of approximations, sorry. We're gonna generate a lot of approximations. And how we compute one approximation? Well, to compute one approximation, what we have to do is just to compute the truth table of the approximation for all the vectors with Hamming weight less than the degree of J. So this is what we are doing here, basically. We try to compute the partial truth table for all the vectors of Hamming weight less than the degree of the polynomial, which is this one. And to do that, we just make a recursive call of the algorithm. So as you can see, since the polynomial tilde j is defined in this way, if you want to compute tilde j, what you are computing at the end is again the parity of the number of solutions of one characteristic polynomial. This characteristics polynomial is just tilde f. So to compute the partial truth table to approximate J, for every vector, you make a recursive call to the same algorithm to compute the parity. Then once you compute the parity, you interpolate the polynomial using the interpolation procedure, and then you store it. Then you do this too many times, and then you do the same again. So for every vector here, whenever I count the number of polynomials, the approximation polynomials that I computed before, such that evaluated in that vector is equal to 0, and whenever the majority of them, is equal to 1, and whenever the majority of them is equal to 1, then I said that my polynomial, the one that I wanted to approximate very precisely, is equal to 1. Otherwise, I will set the value of J on B to 0. And then at the end, what I have to do is just to compute the parity. And then when I have, once I have the parity, I can turn this algorithm into an algorithm. An algorithm computing the parity can be used to solve polynomials. And then the complexity is dominated mainly by the recursive calls. I have to do this many recursive calls, where here T is the time complexity of running the algorithm for an instance of size n, meaning that we have n variables. And then for every recursive calls, we have to solve the same problem with for a system of polynomials of only n1 variables. And then the other main step of the algorithms is just this last step, and it has complexity, which can be written like this. Here at the start, maybe I didn't say this, means that I'm removing all the polynomial factors from the complexity. And then again, what we want to set up the parameters so that T1 is similar to T2. And then if we compute the analysis of the complexity of the algorithm, we came out with a complexity like this, where the exponent is now 0.804. And then for the non-quadratic case, we take this coefficient of D from 5 to 2.7, which is give a better complexity. So this is your algorithm. And then Dinur, I'm going to be very quick here. Basically, we want to compute the parity, but to compute G, the truth table of G here, we don't make recursive calls to the same algorithm, but we basically, we do it in a different way. I'm not going to get into this detail now. It's just a different way to compute this polynomial, the truth table of this polynomial, and then we compute the parity. And then that different way allows us to just to take down the exponent to 0.69, and then the coefficient of D for non-quadratic polynomials down to 2. So which is outperforming both cases your Cruz algorithm. So I didn't went into detail there because I want to get a bit more into details here. So here again, the input polynomials. And here we don't want to produce a lot of approximation of J. What we want to do is the following. We're going to use less parameters, only n and n1. And we're going to repeat this loop just few times, let's say like 4 or 5 times. So we are going to generate random linear combination of the initial polynomials. And we are going to compute the truth table of one approximation polynomials. Remember, to produce this approximation polynomial, we start by taking random linear combination. And this is basically is going to be the truth table of the approximation of J given by these initial random polynomials. To do that, we're going to do the following. We're going to run all vectors in this set. So this set is basically the polynomials. B belongs to the set of vectors of n minus n1 coordinate. and Hamming weight less than D. No worries about this, just a restriction, the Hamming weight. And then C has no restriction, can be whatever here. And then we want to check for which of these vectors are solution to the system of polynomials given by R. And whenever we find a solution, we said, well, the approximation, the value of J tilde of the approximation in this vector B is gonna be 1. Otherwise, there's a mistake here. Otherwise, it's gonna be 0. So if this is not a solution, this is gonna be 0. If this is a solution, this is gonna be 1. And then what we have here is just the partial truth table of J tilde. So we interpolate J tilde, we have the full truth table of only one approximation. And then we go through the truth table of the approximation and we said, well, whenever I find a vector which is equal to where the approximation is equal to 1, I'm gonna do something so that I can find a vector such that not the initial set of polynomials, but the system of polynomials given by the R's is equal to 0. So basically what I'm finding here is a solution to the random linear combinations. And then I said, I keep track of all the vectors of B, C being solution of the random linear combinations. And then whenever I have a BC repeated, I just check it in the initial set of polynomials to see if this is a solution of the original system. If this is not a solution, then I continue my loop. Otherwise, I just stop because I already found a solution. So this is Dinur's 2 algorithm, basically. And as you can see here, we don't have recursive calls as in your clone and in Dinur's 1. Even though I didn't mention it, we have to do a recursive call of another algorithm. But we don't have recursive calls. We just have interpolation, which is basically the computation of a zeta transfer. We have a brute force part, which is very easy to estimate what is the complexity. And we repeat the algorithm a few times. There's a complication on estimating the complexity, and it is on computing how many tests we have to do here. But the Dinur uses a probabilistic argument here, and somehow we can estimate how many we have to check. So at the end, the estimation of the complexity of this algorithm is somehow more clean. And this allows to get a more precise complexity estimation where, as you can see here, we are not removing the polynomial factors out of the complexity. And this is the complexity that was given. So in the practical part, so I don't know how much time do I have, Carlo?
How much do you want?
Like
you can go on
15 minutes.
As long as you wish, but don't worry about that time.
Okay. So we took these four algorithms with expresses on the same framework using the same notation in order to be more easy to compare between them. We also implemented them in C. And something that I wanted to see about these algorithms, since they are probabilistic algorithms, was of course the probability of success. And something we realize in practice is the following. So the probability of success of the algorithm is very overwhelming, meaning that it goes to 1 exponentially fast. It goes exponentially faster to 1, fast to 1 as n grows. So in order to do that, in your cloning Dinur, the set of internal iteration, the many of approximation polynomials we have to generate is given by this number here. But in practice, we realize we can reduce this number a lot and still have a very high probability of success. So for instance, here we can see in this plot, let's say something like, I don't know, for n equal, let's say for n equal 25, we can see that just with 61 internal repetitions, meaning that with only 61 approximation of the polynomial J, we can still have a considerably high probability of success. So in practice, one of our conclusions is that we can reduce a bit the number of internal iterations. And we had a similar plot for Dinur first, similar to this one. And for log-standoff, which is the other algorithm using several approximation of a Boolean function, we had a more fluctuant, let's say, plot, not as beautiful as this one, but still the conclusion was kind of the same. We're going to reduce by a lot the number of internal operation approximation, and still keep considerably high level of probability of success. So Dinur 2 doesn't use many internal approximation. Still, we computed the probability of success, and we saw that this was always greater than 90%. So something to highlight here, we are not computing the probability of success of the parity counting in the case of Bjorklund and Dinur first, but the probability of success of the whole algorithm. So using parity counting to consistency checking to finding the actual solution. So we also measure the number of clock cycles for every of the implementations we did. And something related with the implementation is that we did a proof of concept implementation. We didn't want to be fast in order to perform as many bit operations per clock cycle as we could, but just to have a proof of concept implementation so that we can see like we can have like a fair comparison between the practical and the theoretical complexity here. As you can see, the yellow one it have a different name here, but it's a log-standoff. The blue one is Bjorklund. We are just using here the name of the authors. The red one is the first algorithm of Dinur. The second one is Dinur 2, and the black one is brute force. So as you can see, we couldn't reach too much with the log-standoff because it's very slow, and the complexity, I would say, is almost always higher than the others. But the complexity of Bjorklund and Dinur is somehow similar, even though, yeah, it's quite similar, I would say. And the best one was Dinur's, the second algorithm of Dinur's, and you can see that already for early values of n, like n equal 30, the complexity, the practical complexity of this algorithm is already very similar to brute force. And even though our implementation of brute force is not the most efficient one, it's also a proof of concept implementation of brute force. So okay, so something that I forget to say here, for the polynomial system we want to solve here were quadratic polynomials, where we always guarantee that a solution, they have a solution, only one solution. And also something that we also compute for the same quadratic polynomials, where how the exponent or how the exponential complexity was growing as n was growing. So this is what is shown here in this table. So in the column theoretical, we have the theoretical rate of growth, which is given in the asymptotical formula I just showed before. And here we can see the practical, the experimental rate of growth we computed for the values. We were able to do many solutions, many iterations. And I just want to point out here, for all of them, they are already catching up with brute force, meaning that for every unit we increase n, the complexity of the algorithm is not increasing by 2, but by something smaller. And I want to point out here Dinur 2, which is with its experimental rate of growth is very, very similar to the theoretical one, even for early values of n. And we also use this estimation here and all the numbers we got to estimate from which would be the n such that these algorithms would outperform brute force with our implementation of brute force, and we got the following numbers. So we had that log standoff is going to outperform brute force as long as n is greater than 129. This number is 60 for Bjorklund, 132 for Dinur first, and then 33 for Dinur second. So something I also would like to point out here, the number of internal operations we use here inside these algorithms to compute this rate of growth, and this number here was as little as we needed so that we can guarantee that the probability of finding a solution with this, let's say the first 3 row algorithm, was greater than 2 or 3. So if we were use the full S, then these numbers may be higher here. But then we wouldn't reach too much values of n because, for instance, log standoff was already very slow. And then future work, of course, so future work in the implementation point, from the implementation point of view, would be very nice to have fast implementations here, which I think is a bit challenging, especially the interpolation part. So like how can we pack many bit operation in only clock, I mean, as much as we can, bit operation in clock cycle, in one clock cycle, so we can perform like a fast implementation here. I mean, it's not hard to find a way how to do it with the Cetra transform, but with the other function that we use in the interpolation procedure, it's a bit challenging to see how we can implement it so that in one clock cycle, we can just reach as many bit operations as we can. So it's like an implementation in a specialized hardware would be also very good, especially GPUs. And I would say the main challenge here would be just dealing with the memory access cost. As you can see, for all this algorithm, we have to compute the truth table of a Boolean function. And this truth table has 2 to the n minus n1 entries. So this is already a ton of memory that this algorithm use. So this is a challenge we will have to overcome if we want to have a parallel implementation, for example, in GPUs. And then, of course, again, something that would be really nice to have is if there is a quantum version of these algorithms, or if these ideas can somehow simulate different quantum algorithms for solving Boolean systems with polynomials. And again, here, the main issue would be, I would say, the memory, right? Because these quantum algorithms usually have a polynomial, let's say, amount of memory. And that was all. Thank you for your attention. If there's any question, I'll be glad to answer.